Okay, welcome back. So it's second hour of this EFT lecture series, and the plan is to kind of give you an introduction and then maybe kind of a tour, a whirlwind tour of the standard model as an EFT, so the SMEFT. And there's a fair bit to cover, so we'll see how far we get, depending on time. And let me just start immediately. So of course, we start with the success story of the standard model itself. You've basically seen this plot already in Fabio's colloquium, or some version of it. We found the scalar. We know it couples to mass in some way. And indeed, it behaves very much like the Higgs of the standard model. By looking at these sort of fits of say, ATLAS or CMS data, you see that all of these predictions for the couplings to various particles, they lie around 1. And then we know, of course, at least one ingredient is missing, that's for sure, the Higgs coupling to itself, but also many of the light fermion couplings to the Higgs are unknown. So we still have also some way to go to pin down these precise interactions over here. There's quite some big error bars going around. And so far, however, all of our data is broadly consistent with the standard model expectations. And so the LHC mission continues, going in the direction of precision measurements, but also new physics searches. I think this is probably the best motivation for EFT, as also Fabio showed a similar version of this slide. This one's a little bit more outdated, where you've got all of these popular, less popular models of new physics scenarios that might crop up at the LHC, and these are just lower bounds on the energy scale of the various particles involved. So no signatures so far. And so where is everyone? And maybe are they out of reach? That's a question that we might ask ourselves. Thankfully, the standard model, I think, is a great candidate for an EFT. So if you remember all the principles and the features that we discussed yesterday, it's got a very well understood, as far as we know, low energy theory around the weak scale, parameterized by this electroweak vacuum expectation value of the Higgs. Well-defined set of low energy degrees of freedom, our 5 fermion representations, gauge bosons and Higgs. And the LHC data does indeed indicate a gap to the new physics mass scale between the electroweak scale and this purported new physics mass scale that we're looking for. And I think this is sort of epitomized by this paradigm shift that's happening right now at the energy frontier of BSM searches, where when the LHC started up, we were really looking for this sort of picture, direct searches, nice bump hunt, where some kind of big resonance would just come and slap us in the face and we would just see it. Of course, this hasn't happened, and so we're more and more moving now onto this sort of picture where we're looking for really indirect effects, perhaps in the tails of distributions. And the underlying assumption here is that somehow new physics is heavy. So you've got some resonance at some energy here, which is a little bit out of reach of the LHC, and is causing this indirect effect in the tail of this distribution. And so the combination of precision measurements and heavy new physics lends itself extremely well to this standard model effective field theory paradigm. So as before, we have this operator expansion, identical to the discussions we had yesterday, where indeed you now combine the low energy degrees of freedom of the standard model, making more fields, adding more fields or more derivatives to the dimension 4 operators to make up higher dimensional operators. And what you have to respect this time is the gauge symmetry of the standard model, and which includes also this idea of a linear electroweak symmetry breaking, which just means that the Higgs is really a doublet representation of SU2. And of course, for the standard model gauge symmetries, it means the operators themselves have to be singlets under this entire gauge group. And so you can see this SMEFT indeed as a parameter space for new interactions between all the standard model particles. But with all these nice features of the EFT that we discussed last time. So, symmetries, nice matching prescription, systematic improvability through higher order operators and higher order corrections. So we have our standard model Lagrangian supplemented by successively higher dimensional operator Lagrangians. It turns out at dimension 5 there's only one operator, which is this lepton number violating Weinberg operator for neutrino masses, which Richard might talk about today, I'm not sure. And so dimension 6 turns out to be the lowest sort of non-trivial order in this sense, where you really have a big body of operators that you can work with and parameterize various different types of new interactions between the standard model particles. So this is just to give you a flavor of the kind of things that crop up. You can, of course, convince yourself that all of these things have mass dimension 6 at various different creative combinations of standard model representations, and gauge invariant dimension 6 operators. So if you think about this, for example, you have these 3 field strength tensors, so this is going to be somehow related to the self-coupling of the gauge bosons. This is just a whole bunch of Higgs fields, so this is surely going to affect the Higgs potential, self-coupling of the Higgs. This is essentially a standard model Yukawa term multiplied by this singlet phi dagger phi, so that's somehow going to affect the Higgs fermion interaction. These current operators here, they look a bit funny. They're combinations of currents of SU2 or SU2 gauge currents, and indeed it turns out that they affect things like the gauge fermion interactions. Here you see Higgs's and gauge fields, so that's going to be gauge Higgs. This one turns out to affect the Higgs Z interaction. These are the so-called dipole operators, which can affect either the SU2 or just all of the gauge interactions. They give you a non-standard Lorentz structure between the gauge fields and the quark, left-right quark combination with this sort of funny sigma mu nu structure. And then finally, of course, our well-known 4 fermion operators, which are now the same as our Fermi interaction. So then you can think, well, what are various ways in which I can measure these interactions? And of course, for example, you could look at diboson production for this guy, di-Higgs production for this guy, TTH, H2BB bar for these Yukawa operators. Here you might look at the features of Z and W production on a shell. This one, for example, controls gluon-gluon fusion or Higgs decays, or production indeed, to electroweak states. MZ measurements for this Higgs Z interaction, because this also shifts the mass of the Z with respect to the mass of the W. These dipole interactions can be probed with various types of processes involving the interactions of the fermions and the gauge bosons, and also sometimes the Higgs, because you also have a Higgs field over here. And then for fermions, well, all kinds of scattering processes involving 2 fermions in the initial state and 2 fermions in the final state. Okay, so that was just a quick overview. I'll go into those in a little bit more detail later. So just to show you again, you've seen this table already. This is probably the best summary available online of these types of operators, where indeed the whole dimension 6 basis can be summarized in these 2 tables here. So I showed you an operator of each class, I think, in that last slide. And so you basically just have various combinations of the same structures cropping up, different gauge fields, different fermions, so on. And it turns out that starting from work by Büchner and Weiler in the 80s and then refined by Tchaikovsky et al. In the 2010, this number of independent operators was refined down to 59. If you assume a totally flavor universal structure, so nothing, all of these indices, flavor indices on the fermions have the same coupling, so there's no structure there at all. And that translates to a number of independent real parameters of 76 in the flavor universal case, where all fermion generations have the same coefficient, and 2,499 in the flavor general case. 2,500 degrees of freedom already at dimension 6. So that means every single flavor combination has an independent coefficient in these 2 fermion and 4 fermion operators. So you can see that the main culprits are going to be 4 fermions because they have 81 flavor entries each, 3 times 3 times 3 times 3. Indeed, it turns out that the counting for dimension 8 and above was worked out in a very interesting work by these guys, where they figured out that at dimension 8, for example, this 76 turns into 835, 2,500 turns into 37,000. And then they even showed the numbers all the way up to dimension 15. So they've worked out a very nice mathematical structure to all this stuff. And they confirmed that the number of operators grows exponentially with the number of dimensions. So that was, yes?
So this 4 Fermi operators, like the independent one is only with 1 gamma, and there will be like other.
There are other structures, indeed. So these are the most common ones, the currents. So you have a vector currents coupled together, but you also have scalar currents coupled together here. And you also have tensor operators, but in this basis, I believe they reduce them down using identities, fiats. They rotate them into scalar and vector, basically. Yeah. So indeed, this is called the Warsaw basis. That's what people call it these days, because the guys that refined it are from Poland, from the University of Warsaw. But there are other sometimes used bases which you might have come across in your research if you ever looked into this stuff. In particular, this Silch basis is somewhat used sometimes. Higgs basis, also this HISZ parameterization. I would say that this Warsaw is certainly the most commonly used and commonly accepted parameterization these days. But from our discussion yesterday, we remember that they're all equivalent. So as long as they all include the same number of degrees of freedom, the choice of which specific operators you include is up to you, and in the end, the physical predictions should be the same. And there are tools, such as this Rosetta tool, for example, which can help you translate between the bases in case you might come across 2 different things that you don't really, you have trouble mapping between the two different bases. Okay. So as far as the SMEFT is concerned, the Wilson coefficients are really theory input parameters of the theory. Okay. So they're analogous to the input parameters in the standard model in the end, are well known, alpha strong, alpha lecture weak, so on. Wilson coefficients are equally unknown and need to be determined from data. And so the sort of idea is that this precision program of the LHC will allow us to measure these parameters, these Wilson coefficients, at dimension 6 and perhaps beyond. And the practical sort of upshot is that you're extending the energy reach of your collider to new physics beyond this nominal energy, because in principle these guys have to live slightly beyond your available energy in order for the EFT thing to work. Of course, we then have these SMEFT interactions are going to affect the various scattering processes that we're able to recreate at the LHC in our low energy model of the standard model. So what do we get generally from these operators is, of course, new Lorentz structures, because we have more mass dimension available. So that means contact interactions or operators with lots more derivatives. These can kind of just be understood as an explicit source of energy growth, additional energy growth in scattering amplitudes as a function of, say, kinematic rules. And this is okay. You don't have to worry about it because, okay, this is unitarity violating behavior, of course, but indeed your theory only has a valid validity regime in energy anyway. So you're not going to take the theory up to infinity. You know that there's a cutoff. And so this is really a feature of the theory. It's not, I mean, it's sick or anything. 4 fermion operators are an example of that. Also this triple gauge operator, for example. And then the second thing that can happen sometimes is that you can modify also standard model-like terms. You can shift couplings in the standard model. And this happens because after electric symmetry breaking, where we know that this Higgs field takes a vacuum expectation value, your dimension 6 operators can sometimes get effectively dimensionally reduced down by powers of this vacuum expectation value. So you have this dimension 6 dimension 5 operator, or v squared times an effective dimension 4 operator, which is, of course, the same dimension as the standard model. And so this is most obvious in the case where you've constructed a dimension 6 operator by just taking a standard model term and adding phi dagger phi to it. So that's one class of such dimension 6 operators, the simplest type. So whenever this phi dagger phi takes a vev, then you're effectively left with a standard model interaction term times v squared. Here, of course, there should be a 1 over lambda squared in each one. So there's the Yukawa, for example, or this Higgs potential type 1, or these currents that I mentioned, and also these gauge Higgs type operators. So in each case, you just end up shifting a standard model-like term. So here you modify the Yukawa, the Higgs potential, gauge fermion interactions, gauge kinetic term. All in all, these, as I said, result in a shift of standard model-like interactions, standard model Lorentz structures. One interesting thing that can happen is that these types of shifts can be interpreted to spoil these unitarity cancellations in the standard model. So you may know that in various scattering processes, if you generally parameterize all of the couplings of the standard model without fixing them exactly to their standard model values, and you compute, say, WW scattering or other types, you see that indeed, without specific relations enforced by the standard model gauge symmetry, these and also electroweak symmetry breaking, so masses related to their couplings to the Higgs, then things just start to grow wildly with energy. And so the standard model really regulates the unitarity of the symmetry, and the Higgs mechanism in the standard model really controls the unitarity of the theory. So once you start shifting these guys around, then you end up inducing the unitarity violating energy growth. So energy growth from explicit Lorentz structures, and also potentially energy growth from implicit effects due to these standard model shifts. And then the final annoying technical thing that one has to deal with is that you extract, of course, the standard model inputs themselves, so these other guys, alpha, GF, etc., by comparing several experimental measurements to the theory. And since you're modifying standard model-like interactions, you're also modifying the predictions for these various input measurements. And so the extraction of the standard model inputs themselves now also depends on these Wilson coefficients. So you have to propagate that through. And so I don't want to go into too much detail, but here just a quick example to see how that works. For GF, where we calculated it before, we matched it to the standard model earlier. You know that if we measure muon decay, then this value for GF comes out, which allows us to infer a value for the VEV, 246 GeV. And indeed, there are two types of operators which contribute to this. 4-fermion operator, which is the same as the Fermi operator itself, as well as these two current operators, which actually shift the W boson interactions with the leptons. So that's what I said. Yeah, A contains OF, the Fermi operator. B and C shifts these W couplings like this. And so you have to recompute now because you have a new theory, a SMEFT. You're not working in the standard model anymore, so you have to say, what's my prediction for muon decay? So if you go ahead and work that through, you find that indeed, basically the VEV or GF, the VEV as a function of GF changes and gets modified. And so you have a new relation between these two quantities, which depends on your inputs from this SMEFT as well. And you have to propagate that through to all observables that then depend on this VEV. Because in the end, you fix your VEV by measuring GF, and all of this stuff gets propagated through everywhere. Okay, so now that you have all this information, you're ready to compute observables in this theory to try and constrain it in some way. So if you pick some basis and some appropriate set of symmetries, like flavor structure, maybe to reduce this set of parameters a bit, CP conservation, whatever you like, and then all you have to do is just work out the Feynman rules, calculate a matrix element, some scattering process that you're interested in. And so if you consider a generic contribution from this SMEFT, then it kind of goes like this. So you have the amplitude, for example, as the standard model prediction, plus whatever single operator insertion that you want to put in that affects this particular process. And then if you now square that out into some observable, say a cross-section, then you see that you'll have the standard model contribution and then a generic expansion up to 1 over lambda fourth. So this comes from the square of the standard model piece. This comes from the interference of the standard model piece with the EFT piece. That's the EFT piece there. and this comes from the square of the EFT piece here. And it's no higher than that. And of course, so the leading contribution typically comes from the interference, because it's less suppressed in powers of lambda. That's the idea, right? Our SMEFT is an expansion in 1 over lambda squared, and so you would hope that this would be the most important piece, but that's not necessarily always the case. So one thing that you notice, as I mentioned, that this is formally higher order in the EFT expansion, this squared term, although it's basis independent. So it doesn't matter what basis I express my operators in, a given contribution will be basis independent to this particular term, because this expansion occurs actually at the amplitude level. And so this is thought that it could be subleading, should be subleading, unless some kind of these terms are somehow forbidden or suppressed, some symmetry or some argument that says that this is somehow small for some reason. And this turns out to happen quite often in processes that we're interested in. So often we still compute this just because the information also is available anyway. So why not compute it and see how big it is to understand a bit more about the impact of SMEFT on our given process. And indeed, the importance of this guy with respect to dimension 8 operators, which would also arise at this order, interfering with the standard model, is a somewhat model-dependent statement. Okay, so what's the roadmap for the SMEFT now? We've chosen our basis with some flavor assumptions, some symmetries. We maybe have thought about some processes or observables we'd like to use to constrain it. Could be rate measurements, could be differential, preferably differential, because it allows us to probe the theory at higher energies. Or it could even be some high-level observables like asymmetries, optimal observables, even some neural network output. And then I think the first reasonable thing to do is to conduct a sensitivity study. So just determine the dependence of the Wilson coefficients in this way. And for that, of course, we need precise Monte Carlo tools, which is one of the reasons we're all here. And then once you've done that, you can go and look at the measurement. Hopefully that's been done at the experiment, or you will motivate the experiments to do that measurement. This typically is done in some fiducial volume. So basically, they're not able, of course, to measure things outside of the detector acceptance. But sometimes they do unfold and extrapolate the measurements. But this is always done in the standard model hypothesis. And so one should be careful not to use these extrapolated measurements to constrain this method, because you don't know what the efficiency is for the standard model unless you the EFT, unless you compute it yourself. Anyhow, this is a detail which I probably should have removed. From these measurements, you can then extract limits on some set of coefficients. But really what you want to do is not just individual measurements, of course, or individual operators, but do the global thing. So you take a whole bunch of operators, plug them into a likelihood for all the different Wilson coefficients as a function of the observables. I think this was observables, actually, not operators. And then you do a statistical analysis in some way and extract sort of confidence intervals or contours in this operator space, which is preferred or excluded by the data. And there's various statistical analyses that you can do. And now analyzing this space of operators that's constrained or not allows you to perhaps work out where you have some blind direction, some lack of sensitivity somewhere. And perhaps will even motivate then further measurements, further processes that might help you close various directions in the parameter space. And of course, once you have this global analysis, you can then map to some UV model of choice. Or there might even be some hints of new physics, which would be very interesting and would allow you to perhaps point you in a given direction, because specific models might be more likely to predict the given deviations that you've observed. You can also do this validity analysis. It's very important to do this validity analysis that I kind of gave you a toy example of yesterday, which is an a posteriori exercise that depends really on your sensitivity and is intrinsically model dependent, as I hope I convinced you. So let me now just take you through some applications now that I've given you this intro. How much time do I have left?
Like 20 minutes.
20? Okay, let's see. So let's take this SMEFT and think about specifically the electroweak sector. And I mean that in a broad term, in a broad sense of these three guys. So this is just the picture that Fabio showed in his talk, which he's been advertising for me all over the world. I've got the animated version though, which is even better. So you have these three sectors, huh? The Higgs boson, just discovered at the LHC, very interesting. The top quark, hasn't been discovered for very long, very strongly coupled to the Higgs. Major player in electroweak symmetry breaking, lots of BSM scenarios involving, trying to explain the dynamics of this mechanism, involve the top quark or some top partner or something. Electroweak gauge bosons, which of course are the second most massive guys and couple also quite appreciably to the Higgs. And so there are a whole bunch of different processes that we can use at the LHC to test the various interactions between these guys. So gluon fusion, branching ratios, all of these Higgs quantities, very interesting to look at. And then for the top quark, you have TT bar, 4-top, flavor changing effects. And then on the electroweak side, you have, of course, the well-known precision observables, which actually come from LEP, but also at Drell-Yan at the LHC, triple gauge couplings, so diboson production, essentially. And then you start to have processes which overlap between the two sectors. So, for example, Higgs and electroweak boson couplings, you would think about electroweak Higgs production, vector boson fusion, associated production, vector boson scattering perhaps as well. Higgs on top, TTH is the obvious candidate there. Somehow gluon-gluon fusion is almost in there as well, I would say. Yeah? And then with the top electroweak couplings, you have, for example, single top production, which is a very nice probe of the electroweak couplings of the tops. But also TT plus V, so TTZ, TT gamma, etc. And then you have even more interesting processes which lie right in the middle of this Venn diagram here, which really probe, so single top plus Higgs or Z, this really probes all the different interactions among these three different particles. And then not to mention the fact that there's lots of measurements involving jets, multi-jets, W plus jets, and the decays of various particles, flavor measurements, and of course searches for CP violation as well. So all of these guys can be used in principle, have been used in part to assess the compatibility of the Standard Model EFT hypothesis and measure the coefficients of this theory. So the big news of the year is that we know now that the top couples to the Higgs. So that's very exciting, beautiful diphoton resonance of the Higgs in TTH production, which I never thought I would see, and it's really amazed me when I saw this plot. If some of you remember the 2012, when we really found the initial diphoton peak, didn't think that we would be seeing this same picture in TTH, at least not so soon. So the top definitely now couples to the Higgs, and we can say, well, we had indirect evidence from that before, from this type of process, gluon fusion, but really the direct determination of the top Yukawa via TTH at greater than 5 sigma, this is really a landmark moment, which, as I will show you later on, is extremely important for understanding the couplings between the top and the Higgs and the gluon. So the measurement is consistent with the Standard Model, and it kind of closes this trifecta of electroweak sector, in the sense that we now know that they all interact among each other for sure. So they're all in the game, these players, and the LHC legacy, I think, really will be forged in delivering sector. I think my mic is, well, it's okay. As we know, the Standard Model is a spontaneously broken gauge Yukawa theory that offers really only a parameterization of how this spontaneous breaking occurs, and really lacks a dynamical origin for the weak scale. And it's full of symmetries and relations between different couplings. So these guys, for example, connect the mass of their mass to the coupling of the Higgs. These guys' self-interactions are connected to the gauge currents. It's a beautifully symmetric theory, And there's a delicate balance, as I mentioned earlier, which conserves unitarity and normalizability. And so the SMEFT actually breaks this balance, as I mentioned earlier. And so I think it's interesting to exploit this feature. But let me first take you through really just quickly what the effects of various operators in a little bit more detail, to give you a flavor of what kind of things you can do, and then finish with a couple of applications of this information. So these current operators are interesting because they essentially, you see that if I set the Higgs to its VEV in any of these guys, I end up with a covariant derivative times the current. So essentially, I'm shifting couplings of W's and Z's to fermions. The reason why the photon coupling and the gluon coupling don't get changed is because the U1 charge and the glue SU3 are still good symmetries of the low energy theory. So you're not allowed to shift the couplings of those gauge bosons because the low energy still has those gauge symmetries. Whereas the SU2 cross U1 is spontaneously broken. So the Z and the W, you're allowed to shift these couplings after electroweak symmetry breaking. So this is an effective dimension 4 interaction, which could be seen by, for example, producing these guys on shell and measuring their couplings to various things. However, the fact that it's an effective dimension 4 also implies that there's no energy growth with respect to the standard model, right? You just got the same Lorentz structure as a standard model. So you're just overall rescaling rates, maybe shifting asymmetries a little bit, but no energy growth anyhow. And so these are best measured by precision electroweak measurements on the Z peak, in the case of the Z, for example. So in this case, the LHC doesn't appear to maybe have that much to give. However, the fact that these guys are constructed from gauge invariant operators actually means that these types of contact interactions are also predicted. So if I keep one of the Higgs as dynamical in this operator, then actually I have this 4-point interaction, which is not present, a Lorentz structure that's not present in the standard model, and it's effectively dimension 5. And in fact, you have more, so I could have 2 dynamical Higgses as well. And so this type of interaction indeed can actually mediate, for example, electroweak Higgs production at the LHC. This would be VH, and this would be a VBF-like. So that's very interesting. And it turns out that if you look at diboson production using these operators, that it actually grows with energy, with the power of E squared, the cross-section. No, the amplitude, sorry. And this is strange, right? Because you're using this non-energy growing vertex, but you're obtaining energy growth in the 2-to-2 scattering amplitude. And so this is exactly an example of this unitarity non-cancellation behavior in this FFVV scattering. So the fact that you've broken now the delicate balance between the couplings of the fermions, the self-interactions of the gauge bosons, because there's also an S-channel triple gauge contribution to this scattering, this actually turns out to break unitarity and lead to energy growth that you can measure at colliders. Okay. Gauge coupling, these guys, this is a smaller set of operators which essentially leads to higher derivative self-interactions among the gauge bosons. So 3-point and 4-point, which grow with energy with respect to the standard model. So these are very clean and sort of simple to look for. It's very obvious that you would look at diboson production for this and just look in the tails of the differential distributions and get very nice limits on these operators. And the gluon version also exists. Indeed, we can use things like multi-jet production to constrain this type of operator. And indeed, it's been done. These people looked at various multi-jet measurements and got very, very strong constraints on these operators, to the point where it's unlikely that this operator would contribute appreciably to any other process that it might affect. For example, top production, this guy can also affect TT bar production, but it turns out that the constraints on this are so strong that you can probably let it go. Yes?
The gauge couplings are not.
Yeah, but these are non-standard model Lorentz structures. So the gauge self-interactions of the gluon with fermions, so the QCD current, the coupling of the gluon to the QCD current is not changed. And also the standard model-like self-interactions of the gluon are unchanged. So that gauge symmetry of the low energy QCD part of the Lagrangian is unchanged. However, dimension 6 operators involving Lorentz structures that are not beyond the standard model can still exist. So that's sort of the qualitative difference there. So this has 3 field strengths, right, which doesn't exist in the standard model. So you get triple, quartic, quintic, sextic interactions with the gluons with higher derivatives. And they also have CP violating versions as well. Gauge Higgs is also fairly obvious that you would affect the various couplings of the Higgs boson with the gauge bosons, and so you get these types of interactions here, and you can mediate gluon fusion. So this is really the operator that in the standard model, when you integrate out the top, you get this operator here, and that means Higgs production, di-Higgs production in this case. But also in the electroweak boson side, you have indeed VH, VBF, which all have some degree of growth with respect to the standard model in energy. There's one weird one, which actually leads to a kinetic mixing between the W3 and the B, this guy over here, and is actually related to the S parameter of the electroweak. It actually maps 1-to-1 with the S parameter of the electroweak precision tests, the Peskin-Takeuchi parameters. And he has his friend over here, which is the T parameter. So there are 2 operators in this basis which actually map 1-to-1 with the S and T parameters of the precision measurements, and you can indeed constrain these, which was done in this global fit over here. They also showed a nice plot where they take the S and T parameter observables. These are the constraints from LEP, and if you add constraints from Higgs measurements, you actually get a much nicer, smaller ellipse of allowed parameter space. Again, these guys also have CP violating versions, which you might be interested in looking at. Looking at now the 2 fermion operators, other 2 fermion operators, so Yukawa, I mentioned these guys. They modify the interaction of the Higgs with the fermions, and also predict these types of funny contact interactions. And you have the dipoles also, which again lead to a non-standard model like Lorentz structure between the gauge bosons and the fermions, which means that you can also have photons and gluons in this case, because you're not modifying the standard model structure of the gauge sector. These also predict these funny contact interactions, and also even have this for the non-abelian case, where you have, say, G or W over here. You also have these contact interactions, which give you additional sources of energy growth. And so one interesting place in which these things can occur is when you consider the coupling of the top to the Higgs, you get these indirect effects in gluon-gluon fusion and di-Higgs. Right? And so you see that on this side you can put a dipole operator, on this side you can put the Yukawa operator. So you've got already 2 guys that can enter in the loop in different ways. And on the TTH side, you have the same potentially degenerate effect of these 2 different operators. And so this is kind of highlighting the complementarity between these 2 processes that I mentioned earlier when I introduced the recent measurement of the top, the TTH production. But the weak versions of these dipoles, they can all mediate things like electroweak top production and decay, which have a different energy and helicity structure to the standard model, which allows us to put quite strong limits on them. So just to highlight again how the global approach is important, and to make explicit this connection between TTH and gluon-gluon fusion, this recent measurement breaks a degeneracy in the parameter space of the SMEFT, of the standard model EFT. And that is among the Yukawa dipole operators and the gluon-gluon fusion operator. If you just measure gluon-gluon fusion, then you see that it's sensitive to these 3 different versions. So the Yukawa here, the dipole here, and the direct contact term over here. And TTH has, of course, all 3 different interactions. The same ones can also enter. And it turns out that if you make the measurements of TTH and single Higgs in particular, this is the projected constraints up to the end of the LHC lifetime, where on this axis we have the gluon fusion operator, on this axis we have the Yukawa, here we have the dipole, again here we have the Yukawa. And so if I just make one measurement, pp going to Higgs, that's the blue line, and you see that you have completely degenerate blind directions in this parameter space. So you're unable to truly pin down the constraints in the space. Higgs measurement, this pink band, you see that you're really able to say, okay, well, it's not allowed to be outside of this blue line, but it's also not allowed to be outside of this red line. And so you're really pinning down this parameter space, this three-dimensional parameter space, very strongly by adding this measurement of TTH production. So this kind of, yes, so complementarity is very good for TTH and gluon-gluon fusion in this space of operators. And this highlights the importance of the global approach. How am I doing? 10? Okay. 4 fermion operators, they're kind of like a Pandora's box in the SMEFT in the sense that there's so many of them. There are many different Lorentz structures that can come in, scalar currents, as Ambresh asked about, but also the vector currents, various different group structures, so they can be SU2 singlet currents, SU2 triplet currents, SU3 singlet currents, SU3 octet currents. There's lots of possibilities. And the main thing is that they appear everywhere. But we can somehow control their number by using various flavor assumptions. For the LHC, of course, you probably want at least one of these currents to be QQ bar for it to be interesting. Right? So if you have 4 light quarks, then you might contribute to dijet production, which actually leads to quite strong constraints. If you have 2 leptons on one side, then that's Drell-Yan basically, so also relatively strong constraints. Once you start breaking the flavor symmetry and adding specific couplings to the heavy quarks, then this would be, for example, TT bar production or single top production, and even 4 heavy operators, so 4 top production, TTBB. These are relatively unconstrained because such measurements are not down to the standard model value yet, particularly 4 top has not been measured down to its standard model prediction yet. And they, of course, contribute to different higher point processes, so TTH, TTZ, TTW, all these kinds of processes that you were interested in measuring tend to have some contribution somewhere from a 4 fermion operator. So even if you try and control them, they're always going to appear, and they can sometimes pollute and complicate your fitting procedure if you try to include them as well. So the bosonic part of this basis that I showed you here, this actually covers all possible deviations up to dimension 6 in the gauge Higgs sector. So this covers this connection here. Now, the top is important. We've discussed, as we've discussed, and so we want to be able to include it in its own way. And if you want to do that, then you actually have to go beyond this universal flavor structure assumption that I mentioned before, where you just set all the flavor entries to have the same Wilson coefficient. We have to somehow make the top special. And a good way of doing that is to use flavor symmetries themselves. And so this universal case corresponds to saying that each fermionic representation of the standard model gauge group has its own U3 symmetry, where I can just rotate them in any way, and I don't change anything, right? So if I assign the same coupling to all the generations, you find that the Lagrangian has this symmetry, except for the Yukawa couplings, which actually break this symmetry. And so if I relax this on the doublet quark and right-handed uptype down to U2, so that means that I still have a symmetry between the first 2 generations, but I break it for the 3rd generation. And that allows me to single out independent operators for modified top interactions in a controlled symmetric way, which will be safe in terms of radiative corrections, etc. And so of all of these different classes of operators that I showed you earlier, I essentially just have the same, but with specifically 3rd generation quark and 3rd generation top, and top, right-handed top in each type, in each entry. And so I add some new independent degrees of freedom to my SMEFT, but I'm also able to treat the top separately and kind of complete this picture of the electroweak symmetry breaking sector, at least the 3 important parts of the electroweak symmetry breaking sector. And this is also important because the top quark interactions are not that well known, because the LHC is really the first precision top machine. And so I think it's a very useful thing to do to consider how well we're able to understand the properties of specifically the top quark using the LHC data and its interactions with the various different sectors. So I mentioned that we need precise Monte Carlo tools as well in order to do this exercise, right? And so several tools exist. Here I just wanted to list what was available. At leading order, there's various parameterizations, there are various implementations. Most of them exploit this fine rules UFO structure that you've learned about already. And in some cases, next leading order precision can also be important. You reduce your scale uncertainties and get better predictions for the normalizations and shapes of your SMEFT effects. And also you might have sensitivity that only arises at one loop from a given operator. For example, in the gluon-gluon fusion example, there's a bunch of SMEFT operators that only enter at one loop. So this is useful if you have a relatively weakly constrained direction that could somehow contribute at one loop to a precisely measured observable that might allow you to get competitive or better limits on it than by directly searching for it in tree-level processes. This is really the state of the art, and so NLO-QCD is available, and hopefully in combination with electroweak corrections at some point will provide really the required precision for SMEFT for the duration of the LHC lifetime. So this tool I mentioned is called SMEFT NLO. It's something we're working on, and it's public already in some form, which exploits this fine rules NLO-CT UFO chain and covers all of the different operators in the electroweak sector with this flavor symmetry that singles out the top interactions and can be found here. And it's based on various previous works that looked at specific processes. And the advantage, of course, of this approach is that it's process independent. So you can, once you have the model, you just generate whatever process that you like. That's true of any fine rules model, UFO model. It gives you next leading order accuracy in QCD for any desired process. And we're working on finishing off the 4 fermion operators there as well. On the other side, the full anomalous dimensions matrix, 2,500 by 2,500 dimensional object, is also actually known for the SMEFT, which is a pretty impressive feat, and it was calculated by these guys a few years back. And this also means that now we're able to also make these RG improved predictions where you run the coefficients to various scales and try and assess their impact indirectly like that. And so in particular, you can, for example, run down from the matching scale to your LHC energy, or if you're combining LHC measurements with some other lower energy experiment, you can run between those 2 scales. And also, in particularly interestingly, they allow you to assess the scale uncertainty from varying the scale and seeing how the coefficients change and mix and can quantify this missing higher orders in the perturbative expansion. Here I just wanted to list a bunch of other available tools. Don't want to go into detail there, just in case you're interested, you can have a look. And finally, in the last 5 minutes maybe, I will try and tell you about one application. I think I had 2, but I think I'll probably run out of time before that. And it's actually the fit that Fabio already flashed a couple of slides on in his talk. So on the one side, we have, oh, sorry, actually, no, there was one slide before that, which was the fact, I just wanted to point out that EFT is not just a theorist's playground anymore. The experimental community is actually extremely actively interested in this framework, and they really want to include it as much as possible. And this theory-experiment dialogue is a very important aspect of making that a reality. And indeed, there are an increasing number of EFT interpretations directly in the LHC analyses themselves. So it's not just theorists taking the measurements and doing EFT fits. The collaborations themselves are starting to constrain these operators in various different ways. So here's an example of a TTZ differential measurement of last year, where they constrain some of these operators in this top EFT sector. Also, for example, polarization and spin correlations in TT bar. That's also a very nice measurement that constrains this chromomagnetic dipole operator. So the dipole operator of the top and the gluon, I think it provides the best limit available in the literature on this particular operator. And the Higgs people are also not far behind in looking at various constraints on these gauge Higgs operators. Looking at, for example, here this is an example of a associated production measurement, various PT bins, and allow you to really constrain the parameter space of these gauge Higgs operators. All in all, of course, they're still limited to somewhat small subsets of the space because it's a lot more work for experimentalists who do things properly with thousands of nuisance parameters. It takes a lot more effort for them to come out with limits when your signal model can't be too high dimensional, really, as far as they're concerned. So this is a plot of all the different types of measurements that we could use for a global fit, and indeed were used by this SMEFIT collaboration, of which Fabio is a member, where this is probably the state-of-the-art top EFT fit. There has been another more recent paper as well by some other collaborators with Fabio, which I think is on similar footing to this one. So what does that mean, state-of-the-art? Well, firstly, they use very high precision predictions for the standard model part of the observables. So where available, NLO or NNLO QCD. And even for the SMEFT, they include as much as possible next leading order QCD predictions as well. The space is quite large. 4 fermion guys. And they combine over 100 measurements at 3 energy stages of the LHC. At the 3 energy stages of the LHC. That corresponds to more than 10 different production processes, so TT bar, TTH, TTZ, you see all these different types of processes. So I thought we would just dissect the results in the last couple of minutes, and then I'll stop there. So this is a plot that Fabio already showed, where you have your 34-dimensional space and some limits on this C over lambda quantity, C over lambda squared. You see the lowest bars are better, and they come from the individual constraints. So that's when you set everything else to 0. Just switch that one guy on, set everything else to 0. As we discussed, that's an over-optimistic representation of the limits on this operator, because you really have to include the variation of all the other guys to be fair. And so the gray result is the marginalized result, the global result, where you've allowed for the variation of all the other operators at the same time. And you see that it really relaxes the limit considerably in almost all cases. The blue ones were just some other reference constraints which they gathered from the literature to compare their fit to the existing results. Okay, so that's just what I already said. And if you look at a limit on C over lambda, of course, you can kind of translate that to a new physics scale, which depends on your limit, A, and your Wilson coefficient, C. And so if you set this C to 1, you can kind of relate that to a scale. And so up here you have 0.3 TeV, so only 300 or so GeV. Here you have 1 TeV, and down here you have 3 TeV. So that's kind of the range, the ballpark range of the constraints in terms of an energy scale, assuming the Wilson coefficient is set to 1. And these guys also did essentially the same exercise, where they converted it to a scale as well. And you can see that there's kind of a hierarchy in sensitivity of scales here. And that corresponds essentially to the fact that the measurements on the left come from TT bar and single top, which are very high statistics, precisely measured quantities at the LHC, whereas the ones on the right are affected by rarer top production modes like TTZ, TTV, single top plus Z, 4 top, TTBV. These guys have much smaller cross sections, and so you're not going to get as strong limits on these operators just yet. The worry, of course, is that the scales are still somewhat low, and some of these LHC measurements easily go around or beyond this scale. And so this raises the question of whether the validity criterion is fulfilled in this fit. Again, I emphasize that this is a model-dependent statement. But you might think, okay, probably I should check now, because a lot of these scales seem somewhat low. The good thing is that there's still a lot further to go in terms of data collected. Factor of 30 still available, and so that's good. And in fact, these guys, of course, are honest researchers, and so they also checked tried to assess the various aspects of this validity. And one thing they did was to remove the differential MTT bar data. So the invariant mass distribution in top TT bar production, that's sort of a relatively high energy observable, which I think was probably maybe the only binned information that was used. And so they compared how their results change when you remove this data. So that's the gray to the red. And the blue is when they only include inclusive TT bar data, so removing everything else. And so you see all of the limits on the right-hand side disappear because they were sensitive on non-TT bar inclusive data, whereas these guys just get a little bit worse again. But you see that actually the difference between the gray and the red is not night and day, right? And so that's telling you that a lot of the information is actually not coming from the extra high energy region of these measurements. And finally, the other thing we can check is how important these quadratic terms are, the 1 over lambda to the 4th effects, which formally might be higher order in the expansion. And so this is, I think, probably my last slide. What they did is that the gray corresponds to the full result, I think. Yes, so the gray is the full result up to order lambda 4th. The red is the leading order result up to order lambda 4th. And the blue is NLO, but only up to order lambda squared, 1 over lambda squared. And so if you compare red versus gray, you get the impact of leading order versus next leading order. And if you compare blue versus gray, you get the impact of only including the squared part or also including the quadratic part. And so I think this is what we were assessing at this point. So the blue versus gray, you see that in some cases, indeed, there is actually a significant difference between these two pictures, which means that the sensitivity can be dominantly driven by this quadratic piece. And so this is something that one needs to bear in mind when one does the interpretation and the validity check for a specific model. And in fact, some of these are purely driven by the 1 over lambda 4th because there's no limit when you remove that term. Okay, so I think I'm run out of time, so I just want to say that indeed these global fits have only really considered the top and the Higgs sector in isolation so far, and many more rare electroweak top processes will be accessed at the LHC, and I think it'll be very interesting to combine these processes into a big fit. It's a very timely moment to consider them together. And so maybe I can just skip to my conclusions. I don't know how long that's going to take. Maybe I should use the keyboard. So I was going to show you a whole bunch of stuff. You see, I just had too much stuff to show you, which is too bad because this is also quite interesting. But anyway.
Is that a button end?
I don't know how to do that. It's okay. Oops, it's done. So let me conclude. So EFTs are a powerful tool for new physics searchers, which are very complementary to this direct approach of looking for resonances. And I hope that I've shown you a little bit of how the SMEFT is really thriving at the LHC right now. It's really growing, and there's a lot of people getting more and more interested in it, and that it's really an opportune time to start to consider this electroweak symmetry breaking sector in full. There is an ongoing and quite healthy dialogue between the theory and experiment, which we should cultivate as much as possible, and the tools themselves are now available. And so it's time to do this global top electroweak Higgs fit, which hopefully will give us some new insight into the origin of electroweak symmetry breaking. And I think the roadmap for the future is to, at least in terms of the top quark, is really to start looking at higher energy and rarer top quark production modes, which I wasn't able to convince you of this time, but I'll leave it on the slides for you to have a look in your own time, and you can, of course, ask me at any time. So thank you for your time.
WWW anomalous coupling has a 5th or 6th couplings, but it seems hard to see produce for example, 5th W in the LHC. It should be very small event number.
Probably, yes.
Yeah, because W becomes official and 5th W is very small, for example. So,
yes.
Is it possible but the fifth and the sixth coupling is very exotic. So is it possible to see such a effect?
Okay, that's a good question. Firstly, I think that the way you would search for this would be VBF. So you wouldn't have an off-shell, you wouldn't go for the S channel with, so if you wanted, say, the 5-point coupling, you could do 1W with 4, right? Which would be very off-shell. Or you could do fusion of 2 Ws into 3. So I think that would be that would scale better with the energy of your collider. So I believe these kinds of processes probably at a future collider could be probed. So fusing 2 bosons into a 3 boson or 4 boson final state, maybe click or 100 TeV or 27 TeV and a PP collider. I think you could search for these. I think LHC, the event rate will be a bit too low. LHC cross-section is too low, but a bit more energy, maybe we can do it.
For example, 100.
27 maybe?
27.
I'm not sure, I haven't computed the numbers. Maybe Luca knows better, I don't know.
Thank you very much.
So the total cross-section for a process, it can be expressed as standard model cross-section in the interference term of standard model EFT and the EFT cross-section. So you said that the interference term becomes subleading when it's forbidden or it's suppressed by symmetry or helicity. Could you give an example?
Yes, okay. So normally you would expect the dimension, the 1 over lambda to the 4th term to be subleading if there's no other, nothing else at play, right? But in many cases, this 1 over lambda squared term just doesn't exist because of symmetries of the standard model, for example. So let's say you have CP violating interactions in gauge couplings, gauge Higgs couplings, the standard model, right? And so at inclusive level, the CP, the Higgs gauge couplings are CP conserving. And so the amplitudes don't interfere.
Yes.
And therefore, at the inclusive level, cross-section level, it only enters at 1 over lambda to the 4th. Maybe a simpler example would be flavor change. Flavor change neutral currents, for example, in top decays or something like that. These amplitudes are just 0 in the standard model, and so there is no interference term. The helicity part is a little bit more subtle, and it's related to a very nice paper which I should have cited in this talk, where essentially some people were able to show that in the very high energy limit, a very large class of 2 to 2 scattering amplitudes, say for example 2 fermions and 2 gauge bosons, actually do not interfere when you insert a dimension 6 operator into these amplitudes. The interference goes to 0 in the high energy limit with the standard model. So this was a theorem which used helicity, arguments about the helicity structure of the amplitudes involving a dimension 6 operator versus the amplitudes coming from the standard model. And they showed that they just don't overlap, and so they're not able, the total helicity of the amplitude just don't overlap, and they're not able to interfere in the very high energy limit. So at the LHC, of course, we are not in the infinite energy limit, and so there are finite mass effects and radiative effects also, which give you non-zero terms for these interferences. But there is a good reason to generically expect that in some cases you don't interfere as much as you would like to. And it's also because these new Lorentz structures tend to mediate different helicity states to what the standard model does, and so it sometimes makes it hard to interfere.
One more question. Is there any way that we can generalize when do the dimension 8 operators, they become dominant with respect to dimension 6 operators?
The dimension 6 squared or the dimension 6?
Dimension 6?
I mean, without any good reason, you would always hope that if dimension 8 is generically not, is of the same order as dimension 6, then you're a bit worried about your EFT expansion, right? Because you really want this this E over lambda expansion to be somewhat faithful. So the baseline statement is that you don't want dimension 8 to be important with respect to dimension 6. However,
But
sometimes if you're dominated by the square of dimension 6, for example, then you start to worry about whether dimension 8 might be of the same order. And so there's two things you can do. You can check, so you can add some dimension 8 operators and compute them. I think it's a very process-dependent statement. So you can check. And secondly, you can also look at some explicit models and compute the Wilson coefficients for your dimension 6 operator and that dimension 8 operator, and see if there's some kind of generic structure that you can apply to see whether these dimension 8 would be big or small or suppressed, or what the coefficients themselves would be suppressed or not compared to the dimension 6.
Thank you.
And Richard also, but I don't know where he's going to go.
I have a probably quick question.
No.
Maybe not quick. So can you elaborate a bit more? What's you have a different operator bases, right? The Russell and then the others.
Yes.
So can you elaborate more? What's the advantages and disadvantages of each one, and why people use Russell mostly?
There's a lot of sociological elements to that question. So I would like to say that there's really no difference between them. Okay? They have a couple of practical elements. So for example, there's one very niche thing, which is that electroweak precision tests constrain an 8-dimensional space in this Wilson coefficient if you at LEP, LEP measurements. Now, if you work in the Warsaw basis, there's actually 10 operators that contribute to them. So that means you have a 10-operator space, you apply electroweak precision, you have two blind directions, because you're only able to constrain 8 dimensions. The Silch, on the other hand, removes two of those operators, and so you have a closed set as far as electroweak precision constraints are concerned, and the other two can be directly constrained by Higgs measurements. So of course, in the end, it's the same. Right? If you do the full thing in both cases, you get the same answer. But it's just that some people get attached to bases because they seem more practical for some reason. Like there are other descriptions which try as much as possible to separate electroweak precision measurements, Higgs measurements, because you can kind of play tricks and do that if you want. And so sometimes they become practically easier to work with. I think that's really the only reason that you might favor one basis over another, is if you find it somehow practically easier to work with. But other than that, there's no difference. I mean, it's the same.
Another reason may be the availability of tools.
Exactly. Good point. Yes.
Basically, you're forced using the device.
That's a good point. So what Benjamin just said is that since people have preferences for different bases, the people that develop tools will develop them in a specific basis as well. So if you want to exploit, if you want to use it, then you might have to work in a particular basis. But the idea of this Rosetta tool that I showed is that you might not need to do that. So it'll allow you to interface between different bases and particularly with tools, so that you can just work in a basis-independent way as much as possible.
Okay.
The last question. Richard, okay. Is there anyone else has a question? Anyone else? Okay.
We'll give it to Richard then. If you
First, a comment to the question earlier about when is dimension 8 more important than dimension 6. This can occur in some things like baryon number violation, lepton number violation, which the propagator structure first appears can only be described at lowest order by like dimension 7 or dimension 9. For example, neutrinoless double beta decay. You know, you just have to, this is motivated by, say, left-right symmetric model, you would have so many currents that the only way you can build that operator is starting at dimension 8. So there's no lower operator, or 9, something like that. My question for you is a statement you made just a few minutes ago about the lack of interference between, given a fixed helicity state, you're not going to have interference between standard model and EFT operators. Can you say a little more? Because what I have in mind is I just have a simple 2-to-2 scattering process. Everything's in the left-handed helicity state, and I add a G Fermi operator. Say the standard model diagram, I might be exchanging a W but then the G Fermi operator might be motivated by
Yeah.
sequential standard model W prime.
So you just stated a counterexample of this theorem. So this non-interference theorem, as people refer to it, applies to a specific class of 2 to 2 amplitudes. Specifically, it is, I think it's 2 to 2 amplitudes involving at least one transverse gauge boson. So that's the statement, okay? So as long as you have at least one transverse gauge boson, the helicity structure in the high energy limit does not overlap with that of the standard model. External, yeah. Well, you mentioned 4 fermion operators, which don't apply. This theorem just doesn't apply. They can generically interfere. They have the same helicity structure as the standard model. But it turns out that if you think about these kind of scattering processes with at least one longitudinal gauge boson, that actually covers a lot of the interesting LHC processes for Higgs and weak boson physics. And so it seems like a niche thing, but actually it applies to quite a few important processes for the LHC.